morning everyone and welcome to the NPTEL course Advanced Distribution System Analysis and Operation. We are continuing with our module 9, that is the distribution network resiliency studies, and in the last class we have seen that how you can model or you can make your system resilient against extreme weather event, that is the hurricane or the cyclone. So, today's class will see the wildfire resiliency in the power networks, that is the heating effect. First we have seen the effect of the winds on the power network. Today we will see the effect of the heating because of the wildfires in the power network. So, we will see first the overview of it. Wildfires have caused significant damage and disruption to power system in recent years, and recently California states had witnessed in January 2025 a huge wildfire, and that took so many lives and also destroyed the complete distribution and the power system in that region. Okay. So, the transmission systems are at risk, affecting overall power stability and the reliability. Also, the distribution systems are becoming vulnerable, directly impacting residential, commercial and the industrial users. In 2014, the Department of Energy USA reported that wildfire ranked as the leading cause of power emergencies, averaging 93,000 or 9,33,547 customers affected. Okay? That means in 2014 the published it told that it has already affected 9,33,000 customers. So, you can imagine how much huge impact it has on the distribution system. In 2018, Lawrence Berkeley National Lab in US estimated that $700 million of loss due to the wildfire related damage to transmission and the distribution system between 2000 and 2016. So, also the economic loss, not only you have technical loss or customer loss or human lives loss because of the wildfire, but still you have a economical loss of almost $700 million. That is a huge amount of money. So, we have to consider the wildfire risk as well whenever we will design our distribution network. The frequency and severity of the wildfires are expected to rise, especially in California state, increasing risks to infrastructure and the service continuity. So, these are the few events happened recently in US and all over the India, all over the world, depending upon the wildfire incidents. So, this is the most recent incidents happened in the South California, where almost 4,14,000 people are affected and be without power, and power shuts off by the Southern California Edison due to wildfire risks, and almost 4,54,000 people are under public safety power shut off watch. Okay. Other than that, you have other wildfire incidents as well, and most of them are in California. You can see that is happening in the summer time at the United States, and people are forced to stay without power for few days to few weeks time. Okay. So, what are the impacts of the wildfire on the power system operation? First, we will see the impacts on the generation. The solar power plant generation is affected by heat, soot and smoke. That means, if you have a huge wildfire, that will create a huge amount of smoke. So, that will cover the sun on top of the solar power generation. So, then you will not get solar power plant. So, previously in the hurricane you have at least the DERs, the solar powers, to give the supply for the power your dark customers, that means who are not getting power. But here your solar power generation is also affected because of your wildfire incident. Then the transmission system, physical damage to overhead lines, wooden poles, transformers and the substations. Insulation properties of air gaps are degraded because of the so much heat produced. Arcing may occur from ionized air between lines or to the ground. Capacity of transmission line is reduced due to heat, soot and smoke. So, whenever a transmission line is become heated up, it is already because of the power, it is in heat, it is hot. So, because of that external heat from that flame, it will be heated up more. So, when it is heated up, that means it is touching its thermal limits of breakdown. So, the current carrying capacity or the power carrying capacity of the transmission line will reduce significantly. Okay. Then in the distribution system, physical damage to overhead distribution lines, poles and transformers. That means everything will be burnt out. Okay. And distributed solar power generation is also negatively affected. Then wildfire physics will model the wildfire like we modeled our hurricane as well. So, wildfire risk modeling is complex and uncertain. It can include wildfire spread modeling, that means how the wildfire is spreading through the region, wildfire front properties that involves geometric flame features. That means what is the height of the flame, how fast it is moving forward, how much it is wide. That uncertain things you have to consider while modeling your wildfire risk and wildfire impact modeling. Okay. Wildfire releases heat mainly through radiative and convective heat transfer. Calculating heat fluxes requires knowing the fire front intensity and flame geometry. So, flame geometry and intensity of the fire, that you have to know to see how it is propagated and what is the effect, what is the region affected by your wildfire. A wildfire behaves like a moving heat source with defined length, width and tilt angle relative to the fuel bed. Okay. The rate of spread of a wildfire depends on terrain and the fuel condition. That means in which track it is moving forward, how many dry leaves you have, how many trees you have, how many dry other fuels you have. So, depending upon that level, that will enhance or that will determine how fast your wildfire will propagate through your location. Okay. So, forecasted and grassland areas support faster wildfire spread due to better fuel availability. ROS or the rate of spread can be modeled to understand and predict wildfire behavior in various regions. So, how you can model this rate of spread? So, this is, you can say, the schematic of a wildfire where it is propagating through the y axis. This is the wider or the wide of the wildfire and this is the length of the flame at the z axis. Okay. Depending upon that, the wildfire rate of spread is given by Thomas formula, which is given by this, which depends upon the wind speed, because if the wind is very high, that will even help the flame to go to other regions as well, right. So, it depends upon the wind speed, it depends upon the fuel bulk density, that means how much fuel you have, that means dry leaves you have on that path. If the density is very high, then obviously your spread will be very high. Okay. And K is the constant that is assumed to be 0.07 for wildfire. Now, the fire line intensity is obtained by the Newman formula, which is given by 300 L squared, where L is the flame length. Okay. Considering that the radiative heat flux received by the target M, that means if this is your flame going propagating through the y axis and here you have a tower, let us say you have a distribution pole. So, how much your distribution pole or distribution line is getting heat from that flame is given by this formula, and that heat is coming as a radiative heat flux. So, that is considering the atmospheric transmissivity, flame zone emissivity, Stephen Boltzmann constant, flame zone temperature, solar observability and the distance r. These things will dominate how much heat you will get at the target level. Okay. And also the tilt angle, the distance and the height of the target from the ground. Okay. All of this will dominate, all of this will determine that how much heat will be affected to that component of the power system. So, fire intensity and rate of spread are critical for firefighter safety and effectiveness of the fire lines, obviously. High intensity fast moving fires can overwhelm the fire lines, increase risk to firefighters, delay containment efforts and cause greater damage infrastructure including the power system. Okay. Now, how the wildfire is related with the wind speed. Okay. So, wind speed greatly influence the wildfire intensity and the speed. As I have told, if you have a flame somewhere and you blow that flame with a very high wind, there is a very high chance that flame will fly to another place and there you will see fire. So there is a very high chance of that happens actually when the wildfire occurs, and that is why this California wildfire has become a devastating for the western US or the California region, with fire moving up to 6.7 miles per hour in forest and 14 miles per hour in the grassland. So if this is the wind speed you have, then that will affect your wildfire impacts. Large wildfires driven by wind can cause extensive power outages lasting from hours to weeks. That means more hazards it will cause. High winds have dual effects. They can cool power system components via convective heat transfer, but also push fire fronts close to the infrastructure. So it has positive impact and as well as negative impact. So positive impact is that it will take the heat out from the conductor or from the poles, but it will bring the flame close to you. So both the negative and the positive impact the wind speed has on the wildfire hazard. So modeling wildfire risk requires considering both wind speed and the direction as the probabilistic variable. Okay, that means at which direction the wind is blowing, is it blowing in the opposite side of your component or it is blowing at the towards the side of your component. So depending upon that, not only the speed, also the direction of the speed is required for seeing the wildfire impacts with the wind speed. Monte Carlo simulations again we do for doing the probability distributions. Rayleigh for speed and von Mises for the direction are used for accurate wildfire spread modeling. So everything is probabilistic modeling because everything is not certain, everything is very uncertain and very intermittent. Something may happen, may not happen, wind may blow, may not blow. The wind speed may be 20 meter per second or 25 or 10 meter per second, you do not know. So all the resiliency analysis we do, it is a probabilistic stochastic analysis, and with the same Monte Carlo simulation we will generate various number of scenarios for simulating the different kind of situations. Forecast data from weather stations helps fire managers anticipate wildfire behavior more effectively. So what are the data requirements you have? First is the wildfire regime, refers to the frequency and severity of the wildfire for a given area. Okay, that how frequently a area is experiencing wildfire. That means let us say California, it is experiencing frequent wildfire in every year when the summer comes. Okay. So depending upon that you have to take the resiliency, you have to take the actions. Okay. So changing factors like climate change, land use and the human activities are also altering this regime. That means you have to take that consideration also whenever you will strengthen your grid. Okay. So key factors in wildfire risk modeling include your fuel dryness, that means where this forest is there, forest land or grassland is there, how many dry leaves or dry land is there, dry vegetation is there. So that will is the fuel for your flame, for your fire. So that dryness is required. Ambient temperature affecting cooling rates and the damage severity. Then indices like energy release, burning index and severe fire danger indices that is normally considered at the wildfire resiliency index. So wildfire and the power system strength, which gives and how your power system can stand strong, or what is the component or what is the parameters are affected by your wildfire in the power system. First, wildfire heat affects power grid components, raising conductor temperatures and causing sag, annealing and a reduced tensile strength. Obviously, where hanging from your tower, so if it gets more heat, it is a metal, right, copper or aluminum. So it will become elongated. So the tensile strength at these points will lose and then it will show more sag. Okay. Then this impacts lower conductor ampacity, disrupting optimal power flow and overall grid operation. That I have told that will increase the heat of that or make the conductors more hotter. That means that it will touch the thermal limit of the conductor, though your power flowing is very less, but your it will heat the temperature of the conductor will reach the thermal limit. So you have to reduce the power flow, that will hamper your optimal power flow solution. High temperatures can also shorten the lifespan of the transformer, battery and the generation units. Obviously, if you increase the temperature of a particular component, its life will decrease. Component resilience depends on factors like ignition cause, fire spread, speed, fuel type and the weather conditions. Then the health and condition of each grid component influence its vulnerability to wildfire damage. That means when the fire comes, how much vulnerable is your system. Here also you have to study the fragility curve, that with the fire, with the fuel condition, dry leaves condition, how your wildfire will move forward and how all your poles and wires will be hampered by it. So, that you have to study. Probabilistic and fragility models are used to assess the wildfire impacts and component failure likelihood. That is same as like our hurricane models. Proximity to the fire front is a major risk factor. If you are more close to fire, obviously that will be a bad thing for you, that will worsen your situation. Closer components face higher impact, thus spatial mapping and stochastic fire spread models are essential for accurate risk assessment. So, with this we will see the wildfire fragility curve for overhead distribution lines. So, you can see this is the length of fire and this is the slope of the ground with different wind speed conditions. This is the C1, C2, C3 from 5 kilometer per hour to 75 kilometer per hour with a range of 10 kilometer per hours ranging. So, when your wind speed is very high, that is 75 kilometers per hours, you can see that with very high speed that will sometime is good. That means it will not cause the flame to only propagate, but also extinguish it, because if you blow very high wind then it will extinguish. But if a certain amount of your high wind is there, that means that is not capable or enough to extinguish the fire, even that is helping the fire to propagate. So, that if that is the case, then your fragility curve will shift towards the left, and with the same length of fire you have the higher probability of failure. Okay. Same for your slope. Okay. At the slope as well, if it is at the higher or lower wind speed, but the slope is more, if the slope at the constant slope, if you are lower speed, then at the higher your failure probability will be high. Okay. That you can see from this curve, that if your slope is constant, but if you are sitting at a slope, it is not a flat ground. If it is a sloping ground, then at that time if the wind blows, little wind blows, that will not help the fire to propagate. At that time you need a very high value of wind for fire to propagate in the or move forward. So, at that time for a slope, if the wind is very high, then your failure probability is very low, but it is very high when the wind speed is lower. Okay, that you got it. Now, the next we will see the fuel depth and the fuel aridity index. What is aridity index? That is the dryness in the fuel. So, you can see for the fuel depth, same for the wind speed variation. For a constant fuel depth, if your wind speed is very low, then obviously your probability of failure will be high. Same for your aridity, if you change the aridity, with increasing aridity you will get more probability of failure. Okay? That means your fuels are more dry. So, dry leaves burns very faster and catches also fire very faster. Okay? So, that is the fragility curve for your wildfire indices. So, whenever you will design your system and against the wildfire, we have to think that what is the wind speed it may incur or what it may experience. If it is a very high wind speed, you can see for a very high wind speed, the wildfire, you cannot sustain that wind speed, that will take away or blow away your entire fire. That is even good for the system. But if it is a mild, you can say, wind or little bit moderate value of wind, then that will reduce the resiliency level of your system, and that will help the fire to catch to other areas very easily, and that normally happens. Okay. Then conductor height, if you see that if your conductor height, if you increase the conductor height, then for the same amount of flame length and slopes, your failure probability will decrease. So, if you have a lower conductor or higher conductor, that means you will experience lower probability of failure. But if your conductors are close, that is also fine, because if your tower is here and conductor is very low and you have fire over here, then what will happen? It is a very good chance that the fire will catch the conductor, or it will radiate, the heat wave will directly reach to the conductor level. So, that is quite possible, right. So, if you make your towers very tall, then your conductors will be at the certain height, and then that they will be beyond the reach of the flame heat. So, the how you can design this 3 line of defense for enhancing the wildfire resiliency. First line of defense is that you prevent the wildfire. That means, keep the situation like this, that there will be no wildfire at your location. Second, if there is any wildfire, risk mitigation and proactive responses. If something happens, so do the proactive responses against it. And third line, if already it happened, then do the recovery very fast. So, in the first line of defense, to prevent your wildfire concept or wildfire event at your location, you predict the wildfire, timely detect the fire inducing faults. That means, if any fault occur at your system, that event also called wildfire, means called for wildfire. That means, that will give a spark, and that if that spark drops down to dry leaves, that will catch the fire. Okay. So, if this kind of things happen, timely detect it and extinguish that. Early detection of the wildfire, if something happens and it just started, so just extinguish the fire at the initial level. Grid asset as management, you manage your grid asset little bit far from the forest areas where there is very high chance of occurring wildfires. Then manage the vegetation, that means, keep the vegetation in a proper shape. It is not like the tree will come over your distribution lines. Then a very high chance, if the tree is struck with the lightning, or if the tree is exposed to the fire, then that fire will come to your wire and the distribution pole as well. In the second line of defense, where you want to wildfire risk mitigation and the proactive response, first you have to plan for it before. That means, if you cannot prevent it, so at least plan for the responses when something happens. So, how to do it? You simulate the wildfire scenarios in a good software simulator, okay, and see which hazards you are going to face if something happens. Then de-energization, that means, which portions of your network, if you de-energize it with a small, if a small level of wildfire happens, that it will not affect the customers also in large number, but that is also not even give the fuel to the wildfire. Then suppression tactics, find out how you can suppress the wildfire causes. Wildfire monitoring and tracking, always see at the summer time what is happening in the forest areas, how many dry leaves or dry, you can say, tree trunks, these things are fallen there. Okay. Check it. And the grid operation and management, see the how the grid is operating, and is there any fault or everything is good, is your lines are operating properly. Okay. So, these things we can check. And then the third line of defense, where if something happens, after that how you can recover very fast. First, you can send the recovery logistics to those places. Then energy contingency plans, you can plan that if something happens, then the backup supply, everything should be kept ready. Disaster risk financing and the community engagement. So, you engage everyone, all the services, all the stakeholders to cope up from that wildfire events in the distribution power system. With this, we will end our module 9, that is the resiliency studies, and we have learned that how you can model mathematically any natural hazards which is impacting the distribution systems, and how you can cope up or how you can mitigate those effects for the distribution systems. Okay, thank you.